Well, now we're going to turn our attention to focusing on a slightly new idea of what we would call a one-sided limit. So here's at least the general idea. Let's suppose that this function, pictured over here at the right, is the function h of t. So I have a t-axis down at the bottom. Now, this function, if I wanted to communicate it, would be a piecewise function. And hopefully you should be able to see that if I'm using values of x that are less than or equal to -2, I always get the y value back of -1. And if I'm using values of t that are greater than -2, stretching over to the right, I always have the y value of +2. So this here is a perfectly good formula for it. But what if I was asked the question to find the limit of this function as I approached the value of -2? Well, this is actually going to be a little bit complicated, and I even state down here that this is difficult to answer. And you can think about why. Notice, if I was to imagine again that h of t is a path that I'm going to walk along. If I started over here on the path and I started moving towards the x-coordinate of -2, the y value that I'm getting closer to is, well, this way I'm getting closer to -1. But what if I was walking on the path this way, trying to get closer to the x-coordinate of -2? Well, then the y-coordinate I'd be moving closer towards is, I guess, +2. So notice here, when I move from both directions, I kind of don't end up with a single answer. If I come at this from one side or the other side, I get different answers. And so this is very important and introduces the idea that sometimes I can take a limit or think about giving an answer to a limit by thinking about only coming towards the x or the t value that I'm moving towards from one single side. And so here are the intuitive definitions that we have and the symbols that we're going to be using. We will actually go ahead and write the limit of a function f of x as x approaches a, and notice here I have a little negative sign. This little tiny negative sign up there is actually going to signify this side of the number line. That is, I'm kind of coming out of the negatives as I move towards a value. So it's coming from the left. And this other side I then think about as the positive side. And so if I move towards a value from the positives, that would be coming from the right. So you can see here how I use this phrasing in the definition below. So I say we write this and we say that this means the limit of f of x as x approaches a from the left. Again, that's what the little subtraction there means. And that's equal to L as long as we can make the y values as we approach, or as long as the y values here keep getting closer and closer and closer to L, some final value, every time we keep making our x value scooch closer and closer and closer to the value of, in this case, -2. So we're introducing this idea as we move towards -2, but always from below it. In a very similar way, we can see that if I put the little plus sign there, the only thing that changes is we say we're coming from the right. That is, from the right side of the number line, we're moving backwards. So when I'm on the bottom part of this function here, I'd be moving towards -2 from the left. Over here, I'd be moving towards -2 from the right. So again, the pluses and minuses there are all about where you're coming from, not what direction you're headed. So let's go ahead here really quickly then and take a look at something like example number 6 to try to go ahead and figure out how we would answer questions related to this. So again, we're going to deal with the same function. Let's see what we have. I'm going to be dealing with this function h of t, and I want to find the following 3 limits. Let's start with the first one. What's the limit as I approach -2 from the left? Well, remember, that would be moving along this piece of the function. And as I move this direction, what y value does it look like I'm being led towards? Well, it looks like the y value of -1. What about, though, if I approach -2, little positive sign, so that's from the right? Well, that would be coming from this direction, which means I'd be on this piece of the function. And where am I headed? What y value does it look like I'm being led towards? That's a y value of 2. Well, here's then the interesting question. What then is the limit when, notice here, I don't really specify what side I'm approaching from. Notice that whenever we have this, this is what we would then call a two-sided limit, because it's going to require that we approach this value from both sides, from the left and from the right, at the same time. And we provide the number that we're being led toward. Well, this is kind of strange, because here we've already established that if I approach -2 from both sides, I don't just approach one value. On one side, I approach one number, and on the other side, I approach a different number. So what we would say here is that this limit does not exist. That is, there is no single y value that we approach when we move towards -2 from both directions at the same time. There are two different answers, but there is not one unique answer. And so that limit does not exist. And we'll often abbreviate that. It's a very common abbreviation to just write DNE to provide a shorthand for that. And I kind of recap all of that here in the note below. If a limit does not approach any one real number, then we would say the limit does not exist. What's interesting then is that this leads us to an important theorem. Now, theorems in mathematics, we're going to see a lot of them this semester, but they are big, important ideas that come after. They can be logically deduced from definitions or other theorems and rules and ideas that we have previously identified. So this theorem actually comes from this idea of one-sided and two-sided limits. Here's what it states. Suppose that f is a function whose domain contains an open interval, contains an open interval containing a, with a possibly removed. That is, it's something like this. I, again, can approach -2, maybe from both sides, and I don't necessarily have to have the picture connected here. I don't even necessarily have to have a dot here. I could have two open circles. That's totally okay. But here's really the key. If it's the case that the limit of the function is L, that can be true if and only if, and this right here is a big logical phrase we'll talk about more in just a moment, but this means that if I find that a limit is equal to something, then that means that the limit from the left side and the limit from the right side also have to equal the same value. Now, if you think about this, this actually makes a lot of sense, because if I had something maybe like a picture like this, where I said I want to approach 2, and I said if I approach 2 on this function, notice whether I come at it from the left side or from the right side, I get the value 4. And so when I come at it from both sides, I get the value 4. Everything should be the same if this limit here is going to exist. That is, if it's going to have a value. So what this then means is that I have a nice way now of checking to see if limits maybe do not exist. So as it states here in the note, this theorem provides us with a way to prove that a limit does not exist. In particular, if I find that the limit from the left and the limit from the right are not the same, kind of like what we saw up here in this example, coming at this function from one direction and another gave us two different answers. If these two things are not the same, then that means, the overall limit can't have a single real number value, and so it does not exist. So this is a really powerful theorem, and it's actually one of our really, really big ideas of this section, and we'll see how we use that, as well as many of these ideas that we've discussed already, in example number 7, which we'll cover in the next video.